We're going to start with Prim's algorithm, which is a greedy algorithm. But in order to talk about it, we're going to have to first talk about what minimum spanning tree is. So a spanning tree of an undirected connected graph is its connected acyclic subgraph that contains all vertices of the graph. If the graph has weights assigned to its edges, a minimum spanning tree, or MST, is a spanning tree that has the smallest weight of all other spanning trees of the graph, where weight is defined as sum of weights on all edges. And so in this image that I have a graph with 4 vertices, and each of the vertices are connected by at least one edge. Some of them have 2 edges or more. And so a spanning tree of this particular graph would be a path that connects all the vertices but doesn't necessarily have all the edges. In fact, it wouldn't have all the edges. And so, for example, I can have one of the spanning trees of this given graph would be B to D at cost 11, B to C at cost 4, and A to C at cost 10. And so the weight of this particular spanning tree, we would just add up these edges, which would be 25. A different spanning tree could be B to D cost 11, B to C cost 4, and then A to C cost 12. Well, this particular spanning tree is going to be cost of 27. And then another example is A to B, cost of 5, B to D, cost of 11, D to C, cost of 5. The cost of this one would be 21. So minimum spanning tree is going to be the lowest cost of all possible spanning trees. So I have a drawing of every possible spanning tree of this particular graph. And if you added up all the weights of each spanning tree, you would find that the smallest weight spanning tree, or minimum spanning tree, is B to A at cost of 5, B to C at cost of 4, and D to C at cost of 5. So that's going to be 14. And so that is the minimum spanning tree, or MST, of this graph. So this is exactly what Prim's is trying to find is the minimum spanning tree. So I'm going to go through an example with a similar graph to the one I just showed you. I have 4 vertices, B, D, A, C. There's an edge from B to D, cost 11, D to C costs 5, B to A costs 5, A to C costs 10, but A to C has another edge, cost of 12. And there's also an edge from B to C, cost of 4. And then there's also 2 loops. There's a loop going from D to D, cost of 4, and A to A, cost of 8. And so a spanning tree of this particular graph, or I should say a minimum spanning tree, let me just write MST. MST, the number of vertices is going to be the same number of vertices that's in the input. The number of edges in a minimum spanning tree is going to be the number of vertices minus 1. And so that's going to be, in this graph, that's going to be 3. And so actually this algorithm is going to continue until we have 3 edges in the minimum spanning tree solution set. Okay, let's go through the steps. So step 1 is going to be to get rid of loops. So I'm just going to write remove loops. And so that removes this edge that's a loop at D of cost of 4 and the edge at A, which was cost of 8. Step 2 is to get rid of parallel edges. What does that mean? That means two edges that are connecting the same set of vertices. So A to C has two edges, an edge with 10 and an edge with 12. And of course you're going to remove the higher cost edge. So I'm removing edge A to C with 12, cost of 12. Step 3 is to create a set VT. And VT is going to contain the vertices that are in the solution already. And we start VT by placing one of the vertices in VT. It really doesn't matter which one, so I'm just going to go alphabetically and choose A. So A is inside of VT. Okay, and step 4 is to create the MST solution. That's our output set. Your book calls this ET, so it contains the edges in the solution. Sometimes I say MST solution, sometimes I put ET. Okay, but it's the same thing. So ET is going to start out being equal to an empty set, because right now we have no edges in our MST solution. Step 5 is the part that we're going to repeat. Okay, and we're going to repeat until the number of edges in the solution, so I'm going to put NET, is equal to V minus 1, which for us is 3. Okay. Now, what we're going to do that's going to be repeating is we're going to find a minimum weight edge in E, which E contains it's our set of all our edges and their weights. Okay, so we're going to find a minimum weight edge in E that contains one vertex that is in VT and one vertex that is in V minus VT. Okay, so what that means is we're going to choose, whoa, that's really bold. Let's go back here. Choose one vertex in VT and one vertex in V minus VT that has the smallest weight or cost, whatever you want to call it. Okay, VT we said has A in it. So what does V have in it? Well, V is our original set of vertices. So it's A, B, C, and D. So this means that our first edge has to contain A, and then it has to be also contain V minus A. So in other words, B, C, D, everything but A. So we need to choose an edge that definitely contains A, and then either B, C, or D that has the smallest weight. So the only two edges that are adjacent to A is the edge AB with cost of 5 or AC with cost of 10. So we're going to choose the smallest weight, so that's AB with cost of 5. So that means we get to add to our solution. So ET now equals, we're adding an edge, AB 5. And we know that is in our solution. And remember, we're going to end up with 3 edges in our solution. Okay, great. So now that also changes what VT is. So I'm going to write and keep updating VT down here in the bottom left of my screen. So VT now contains A, and it also now contains B. B is also in our solution. All right, and so we're going to keep doing this until the number of edges is 3. So we're going to repeat this again. Choose one vertex in VT, so either A or B, and then another vertex that's V minus VT. So the other vertex has to be either C or D. Okay, so we are going to be comparing 3 different edges. Edge BD is 11, edge BC is 4, edge AC is 10. Well, the smallest weight of those 3 is going to be edge BC with 4. So BC4 is going to be our next edge that we add. BC4. Which means that we now will have C in our solution our vertex solution set, and we have 2 edges now, which is not 3, so we repeat again. Choose one vertex in VT, so either A, B, or C, and another vertex in V minus VT, which means it has to contain D. So either A, B, or C, and then D. So really we're only comparing 2 edges here, because A does not have an edge to D. So we're going to be comparing BD, cost of 11, and CD, cost of 5. Okay, so cost of 5, CD, is going to be what we choose. CD5. And so now D is added to our solution set of vertices, and CD5 was added to our MST solution, and that is 3 edges that are in the solution. So this is our answer, and this is what would be outputted as the solution set of edges. Our minimum spanning tree is AB with 5, BC with 4, and CD with 5. And if we add up those edges, again, that's going to be 14. So it has cost of 14. So that's Prim's algorithm. Okay, I have an in-class practice that I want you all to try out. So I want you to find the minimum spanning tree using Prim's algorithm with this graph. You have vertex A and vertex C. There's an edge between A and C with cost of 1. Vertex A to vertex B, and there's an edge between A and B with cost of 3. B to C has an edge with cost of 4. There's also a vertex D, as in dog. C to D has edge weight of 6, and B has an edge to D of weight of 5. And then there's one more vertex E. There's an edge from D to E, cost of 2. There's an edge from C to E, cost of 7. I have the algorithm for the pseudocode for Prims on the screen now, and it's very kind of high level. I think there's a lot of steps that actually happens in each one of these lines, but At the top, you can see that they use VT for the set of tree vertices that are in the solution. And it is initialized with, it says any vertex, but it starts with V0. And then they have the solution set, which is ET, set to the empty set. And then for I equals 1 to V minus 1, do the following. So find a minimum weight edge, E star is equal to V star comma U star among all the edges, V, U, such that V is in VT and U is in V minus VT. And then they update the solution list of vertices and update the minimum spanning tree solution with that vertex and with that edge. And at the end, that's what is the repeating part. And then after that for loop completes, then we return the solution, which is ET. And then the time efficiency. So the time efficiency of Prim's algorithm depends on the data structures used to implement the algorithm. So if you use an adjacency matrix and a priority queue array, the efficiency would be big theta of the number of vertices squared. If you use a adjacency matrix, which would be a weight matrix, and a minimum heap, the efficiency, oops, spelled that wrong. Let me spell that right. Is big O of the number of edges multiplied by the log of the number of vertices. All right, and that's all of Prim's.